Okay, let's dive right in. If you are knee-deep in exam prep right now, you are in the exact right place. This is our explainer for the ninth major topic in your Mathematics 1 series, linear maps. And we're going to do things a bit differently today. We aren't just going to look at matrices as dry columns of numbers, we're going to see them in action. By the end, you won't just know how to score full marks on your exam, but you'll see exactly why this stuff is absolutely indispensable for your future engineering career. Here is our roadmap for today. First, matrices as geometric transformations. Second, the strict rules of linearity. Third, exam prep, proving linearity. Fourth, setup, the reflection matrix. Fifth, changing your perspective. And finally, engineering relevance and a quick recap. Let's kick things off with Section 1, matrices as geometric transformations. Before you start blindly memorizing formulas, you really need to shift your perspective. Matrices are absolutely not passive tables. Try to visualize this. They are active verbs. Every matrix is like a little machine that takes space and actively manipulates it. It can rotate a whole bridge structure. It can mirror force ratios, project 3D models onto a 2D plane, or even mathematically stretch materials. And this brilliantly illustrates why linear algebra is such a game changer. You can predict an incredibly complex spatial movement exactly just by looking at the numbers in the matrix entries. Every column is literally telling you, hey, this is exactly where the basis factors land after the transformation. Keep that in mind, and all this calculation suddenly makes total sense. Moving right along to Section 2, the rules of linearity. Now, for the exam, intuition alone won't cut it. We need the strict, formal definition of a linear map. Why are these so important anyway? Well, the real world out there is chaotic and totally nonlinear. Just think of a heavy bowling ball hanging from a tiny pen spring. Good old Hooke's law breaks down immediately there. But linear maps are these wonderfully reliable, predictable approximations. We rely on them constantly in civil and mechanical engineering because they preserve structure. So the crucial point for your exam is this. A mapping is only linear if it meets two very specific conditions. This is your ultimate checklist. First, we have homogeneity. This means if I stretch a vector by a certain factor, say alpha, and then transform it, it has to be exactly the same as if I transformed it first and then stretched the result. And second, additivity. Transforming the sum of two vectors must give the exact same result as adding their individual transformations together. Tick both those boxes and you've officially got a linear map. And here is where the magic happens. Once you've proven that a function follows those two golden rules, you can squeeze that entire function, no matter how messy it looks, into a single compact transformation matrix. Toss any vector into it and boom, it's perfectly transformed. All right, Section 3, exam prep, proving linearity. Let's step out of the theory and into the trenches. Let's look directly at these handwritten notes from the source material. The classic exam task, prove whether this is a linear map. Take the very first example, f of x equals 3x plus 2. We test homogeneity. F of alpha times x is simply 3 times alpha times x plus 2, right? But what happens when we calculate alpha times f of x? We bracket the f of x and multiply the whole thing by alpha. Suddenly, we get 3 times alpha times x plus 2 times alpha. And just like that, the results don't match. That sneaky little constant, that plus 2, completely destroys the linearity. It fails. Compare that to a clean linear function, like f of x and y equals 3x plus y. That one breezes through both conditions. It's your standard linear map. But heads up, the second you see powers, like this g of xy equals x squared and y squared, alarm bells should be ringing in your head. Because of the square, your scalar alpha pulls out as alpha squared. Again, homogeneity is ruined. A quick tip for the test. Always write these proofs out step by step with x1, x2, and alpha. That's how you lock in those guaranteed points. Which brings us to Section 4, setup, the reflection matrix. Now we know how to check if something is linear. But here is a super common exam question you will definitely see. How do we actually construct a specific transformation matrix for a reflection? Let's solve this puzzle together. Now, what's really interesting about this image here is how elegantly the visual geometry translates directly into an algebraic formula. Look at the red and green sketch. If you want to reflect a point across an axis, you can actually solve that by first doing a projection onto that very axis. And the formula for that is brilliantly simple. S equals 2p minus e. The S stands for your reflection. P is the projection matrix. meaning P takes you halfway there, right onto the mirror. If you double that, so 2P, you shoot right through the mirror to the exact opposite side. Then you just have to subtract your original starting vector, which is our identity matrix E. Oh, and here's a great sanity check for your exam. If you perform two reflections back to back, so S squared, you absolutely have to land back at E. You return exactly to where you started. Moving on to Section 5, Changing Your Perspective. Sometimes standard coordinate systems are just incredibly awkward for our calculations. Imagine you need to calculate the structural load for a steeply pitched roof. Doing that in standard XY coordinates is a total nightmare. Wouldn't it be way smarter to just rotate the coordinate system so it lines up perfectly with the angle of the roof? That's exactly what the change of basis does. It acts as your mathematical translator into a much more convenient system. And here is the formula you're going to see in almost every exam. A sub v equals v inverse times a sub e times v. I know it looks a bit wild, but it's basically just a classic sandwich multiplication. On the far right, you take your convenient starting coordinates and translate them back into the standard system using the basis matrix V. In the middle, you perform the actual transformation, a sub e. And finally, on the far left, you grab the inverse, v to the power of -1, and translate the result back into your convenient system. It's literally like translating into another language, solving the problem, and translating back. Pretty cool, right? And that brings us to Section 6, Engineering Relevance and Recap. Okay, let's lock in the most important takeaways for your exam. First, matrices are actions, not rigid grids. Second, to prove linearity, you strictly show homogeneity and additivity. Third, for reflections, memorize the trick S equals 2P minus E. And fourth, when a problem is sitting awkwardly in space, use the change of basis as your translator. Master these and you are going to be in great shape. But why put ourselves through all this? Because this is exactly how mechanical and civil engineers operate in the real world. Think about coordinate transformations between local structural components and global reference frames. If you calculate the stress on a single twisted steel beam, you have to somehow translate those local forces into the global model of, say, a massive skyscraper. Without linear algebra and change of basis matrices, well, the structural integrity would collapse pretty fast. Linear maps basically give you the absolute power to control and calculate 3D space. So if a simple grid of numbers actually holds the blueprint to manipulate space itself, what kind of incredible structures are you going to build with them in your career? Think about that. Best of luck with your studying. Thanks for tuning into this explainer, and we will see you next time.